Hello students, welcome again to this online lecture class on the subject area of industrial metallurgy, physical metallurgy, and for the past three classes we have been discussing about heat treatment processes. In the previous class we had taken up what is meant by annealing processes, and we discussed in detail one of the most important annealing processes, which is called full annealing. Today we would discuss two more annealing processes. So I've written annealing part 2. So one of the processes that I'll discuss with you would be spheroidization annealing, and there is another which is called isothermal annealing or cycle annealing. So this slide shows the contents that would be covered, that what is the aim in mind when we give spheroidization annealing treatment to any steel, and why spheroidization annealing treatment is only given to high carbon steels. The reason is that every composition of steel in a particular state with a particular type of a microstructure would give you best machinability when it would have some good combination of softness, hardness, ductility in it. So we'll discuss as to what type of a state, what type of a microstructure is best for machinability in different steel compositions. Then spheroidization, we'll see, that is given to high carbon steels and to alloy tool steels. So here we'll see that what are the different processing routes through which spheroidization heat treatment can be given to high carbon steels or alloy tool steels. Finally, we'll also try to discuss as to why for low carbon steels spheroidization annealing treatment should not be given. After completing spheroidizing, we'll come to the next heat treatment process, the next annealing treatment process, which is called isothermal annealing, and we'll see that this is just a modification over the earlier discussed annealing process, that was full annealing. So what are the objectives of isothermal annealing? What is the procedure that is followed for isothermal annealing of steels? And finally, what are the main benefits and also some of the limitations of isothermal annealing process? Okay, so what is the purpose of spheroidization annealing or spheroidizing? See students, in the next slide we'll realize that if it is a high carbon steel or an alloy tool steel, which obviously again would be high carbon containing steel only, for them inherently the hardness is higher than what is required for good machinability. So high carbon steels or tool steels would require that please give us some heat treatment by virtue of which our inherent hardness decreases to some extent, and there spheroidization annealing comes to picture. So books would say, or even I would say, that this treatment is given to provide good machinability to high carbon steels or alloy tool steels. But how do we achieve this objective? The objective is achieved because see, inherently any high carbon steel or any high alloy tool steel would have high hardness. The steel would be very brittle because of this high hardness, and its machinability would not be good. So what you'll have to do is you'll have to bring about changes in its microstructure so that the steel becomes soft. It induces some softness and ductility in it so that we can reduce its brittleness, we can avoid the cutting tool striking against the hard phases, and then machinability automatically would become good. And how do we achieve it in case of high carbon steel? See, high carbon steels generally would have perlitic structure in them, along with some pro-eutectoid cementite or some carbides like molybdenum carbide, tungsten carbide, titanium carbide, or any other type. Other carbides can be present depending upon the alloying that has been done in the steel. So now if your high carbon steel has got this lamellar type of a cementite present in it, students, cementite is a very hard phase. So when the cutting would start, every time your cutting tool encounters this hard cementite phase, the force that would be required for machining and then the resulting surface finish that you will achieve through machining would not be good. The forces required would be large, the surface finish that would be achieved would be low, and you'll say, sir, machinability of a high carbon steel is not good. In fact, what is the reason? The microstructure is not conducive for good machining. What is the problem with the microstructure? This lamellar cementite or any other form of carbides present, they are creating trouble for the cutting tool to move, for the dislocations to move. So what does spheroidization annealing do for you? Spheroidization annealing would not change the phases that are present. It would not change the volume fraction of the constituent phases. It would only target the cementite phases or any carbide phases morphology. Means whatever cementite or any other carbide is present in a non-spheroidal or non-globular form, it can be present in lamellar form. Cementite and carbides may be present in a lamellar form. They may be present in a needle type form. They can be present in any form. But once spheroidization annealing has been given to the high carbon steels, whatever cementite or carbides are present in them will change to a globular form. So here you can see that this is the microstructure of some typical high carbon steel, a hyper-eutectoid steel or any high alloy steel. And what I can see is this white portion is eutectoid ferrite. These small lamellas, thin lamellas, wide lamella is of eutectoid ferrite. The thin lamellas are of eutectoid cementite. And here typically the cementite has got a lamellar type of a shape, lamellar type of a morphology. And in addition to these two phases, some molybdenum carbide is also present in some of these needle or acicular type of a morphology. You subject this structure, this steel component, to spheroidizing or spheroidization annealing. After it has received the annealing process, all this lamellar cementite, all this any shaped carbide, they all will transform into a globular or spheroidal form. So you can see molybdenum, which was needle type, becomes globular. You can see this cementite, which was lamellar, again changes to globular. So here initially, when you try to machine this type of a microstructure, this type of a steel, as the cutting tool moves, the dislocations face this hard cementite lamella, and the steel component starts demanding a high cutting force. Also, when machining has occurred, the surface that would get generated, the machined surface, would not have low value of roughness. It would be very rough. So ultimately you will conclude, sir, machinability of this steel is not good. So what we are trying to do through spheroidization annealing is we are trying to change the morphology of cementite. So once spheroidization annealing has been given, as the cutting tool now moves, because of the absence of any lamellar type of cementite, there is less obstruction given to the movement of the dislocations. Very good machinability would occur. So that's the objective of spheroidization annealing. What's the objective? We have to change the morphology or the shape of the cementite phase or any other carbide phases which are present in the high carbon steel or alloy tool steels, and we have to essentially bring them into a globular or a spheroidal form. And by what would happen through that, when you try to machine this type of a steel with this type of a microstructure, the cutting tool and the dislocations would very easily move. They would bypass the cementite or carbide phases on most of the occasions. Very good finish would be obtained with very less of force. Machinability would become excellent. But students, it's not every type of steel whose machinability can be improved by spheroidization annealing. I told you in the beginning of this class that machinability of any steel is a function of its composition and the microstructure that is present. Now, inherently, every steel with some value of hardness and softness, with some value of ductility, when these two properties, hardness and ductility, lie in some optimum range, machinability would become excellent. If a steel is too soft, you need to give it a processing which increases its hardness. If a steel is too hard, in order to improve upon its machinability, you have to give it a treatment which reduces its inherent hardness. So microstructural changes have to be done, but they have to be done very judiciously. You cannot take a low carbon steel and make it more softer. It is already very soft. For good machinability, it has to be made slightly harder. Similarly, you cannot take a high carbon steel and make it more harder through some treatment. No, it has to be made slightly softer. Treatment has to be given which makes it slightly softer so that hardness and ductility of the steel composition comes in some optimum range, providing it good machinability. Generally, the conclusion is that any low carbon steel which is inherently soft, treatment has to be given to improve machinability, which can increase their hardness slightly. And for high carbon steels which are inherently very hard, treatment to improve the machinability has to be such that which reduces their hardness and brings them to that optimum range of hardness and ductility so that machinability becomes good. So in the next slide, I'll try to show you that which type of steel composition with what type of processing and microstructure gives best machinability. So we start with very low carbon steels. So whenever any low carbon steel is taken, generally the steel would be very soft and it would say, sir, give me a processing which makes me slightly harder, then my machinability would be good. So what would you do when a low carbon steel of carbon content in this range comes to you and requests you to improve upon its machinability? Spheroidization is not required now. You need to give it a treatment which improves or increases its hardness. And what you will do is you will make its grain structure very fine so that hardness increases, because hardness increases, students, with fine grained structure. And then either make the grains very fine or at least get elongated grains which ultimately break into small grains. And how can we achieve this type of a state, this type of a microstructure in the steel? Please give it plastic deformation or cold working. What is plastic deformation? If cold working, what is cold working? If plastic deformation is given to a steel component at a temperature which is less than 30% of its solidus temperature, then that type of plastic deformation is called cold working process. And through cold working, the grains will get elongated. If the cold working is further increased, those grains would break down into still smaller grains, and that would ultimately improve upon the hardness of these low carbon steels, low hardness steels, and would provide them best machinability. तो अगर आपसे कोई पूछता है कि इस कार्बन कंटेंट वाली स्टील, लो कार्बन स्टील आपके पास आई हुई है और आप उसकी मशीनेबिलिटी सुधारना चाहते हो, किस स्टेट में, किस तरह की स्टेट में, किस तरह के माइक्रोस्ट्रक्चर कंडीशन में इसकी हार्डनेबिलिटी सुधरेगी, आप कहिए सर आप ऐसी स्टील्स को कोल्ड वर्किंग दे दीजिए जिससे उसके अंदर फाइन ग्रेन स्ट्रक्चर आ जाए या इलेक्ट्रॉनिक elongated grains वाला स्ट्रक्चर आ जाए, their machinability would become excellent. Similarly, students, if you had, okay, let me change the color of this is not that legible. Similarly, if somebody asks you that we have a steel with a carbon content of 0.2 to 0.3 weight percentage carbon, and we wish to bring it into a state where its machinability is excellent. So students, for these type of steels, it has been seen, if these steels have got fine grains with very fine lamellar spacing per light, their machinability would become excellent. But if the size of the component is small and is only up to 3 inches in diameter, say if we are talking about a component with circular cross section, so for small sized components, give normalizing heat treatment, you will get this type of a structure, fine grains, perlite with fine lamellar spacing, machinability would become excellent. But somehow if the size is large, then again you can resort to plastic deformation. When you give plastic deformation, you give stretching, you hammer, right? Grains can elongate, grains will become small, hardness would increase slightly, machinability would become excellent. Now, beyond this carbon content, if we start talking about 0.3 to 0.4 weight percentage carbon, these steels inherently have slightly more hardness than what is required for good machinability. So we need to give them a treatment which slightly reduces their hardness. And what do we give them, students? We give them full annealing. What would full annealing give them? Full annealing would bring, as we saw in the previous class, fine grains in them with coarse lamellar perlitic structure. and this structure would slightly reduce their hardness, would induce softness and ductility in them. That is what was required for their better machinability. The purpose would be fulfilled. Then 0.4 to 0.6 weight percentage carbon steels. See, practically speaking, if the carbon content is on the lower side, 0.4, 0.45, give them full annealing. If it is on the higher side, 0.55, 0.6, 0.5, give them spheroidization annealing treatment. But theoretically, if we can somehow get a mix of these two type of microstructures, means we can have fine grained, fine lamellar perlite with again fine grained coarse lamellar perlite. 50% microstructure consists of this, 50% microstructure consists of this, means 50% microstructure is that what comes through normalizing, and 50% microstructure comes through what comes through full annealing. Then the best machinability would come. But this is only a theoretical concept. Ideally, you cannot give a processing route whereby you get 50% coarse lamellar perlitic structure and the remaining 50% fine lamellar perlitic structure. So depending upon where is the carbon content of the steel, if on this side, give it full annealing, if on the higher side, give it spheroidization annealing. And now we come to the composition, students, for which this discussion is being made, that if the steel is a high carbon steel, the steel has got about more than 0.6 weight percentage in it, and maximum for machinability the carbon content can be as high as 1.1 or 1.2 weight percentage. So steels with carbon content in this range, 0.6 to 1.2, or any other alloy steels, alloy tool steels, they have to be, their hardness has to be considerably decreased so that they get the optimum combination of hardness and ductility, so that their machinability becomes maximum, becomes very, very good. And that comes through globular type of cementite embedded in a matrix of ferrite. So for these type of steels, if their machinability has to be improved, we have to reduce their hardness, because they are inherently very, very hard. And what is the way of reducing their hardness? Any cementite, any carbide phase present in them, whatever morphology it is having, please change its morphology, please change the shape of cementite phase, any carbide's shape, to globular or spheroidal form embedded in the beautiful ferrite matrix. So if you can somehow bring, I'm not showing grains over here, if this is your ferrite matrix and you do not have any lamellar or any other morphology for cementite and carbide, rather they come in this form, students' machinability would become tremendously high. So that's the aim of spheroidization annealing, to bring this fine grained structure with fine globular or spheroidal cementite or any other carbide present in ferrite matrix in the microstructure. So let's now see as to how this type of a microstructure can be obtained in high carbon steels or alloy tool steels, for which spheroidization annealing should be given. This is the first route that is available, method 1. But minded, this method is very, very time consuming, very low in productivity. So this is a method, but practically it is not followed in the industry. And this is essentially a subcritical annealing process. Subcritical annealing, that during heat treatment, during annealing, the heat treatment temperature is not till the lower critical temperature. We will remain below the lower critical temperature. So here you can see that we take the steel from room temperature to a temperature which is close to the lower critical temperature of the steel. 1 second, students. Close to the lower critical temperature of the steel, but below it, you have to hold the steel at this temperature for a very long period of time. And what is happening during that long period of time, soaking at this high a temperature? This is the heat treatment temperature, students, annealing temperature, very close to the LCT, but slightly below it, slightly below than it. Hold it. See this perlitic structure. we had ferrite and cementite structure, lamellar structure that is becoming thermodynamically unstable at the heat treatment temperature because of this prolonged heating. And when this prolonged heating is completed and you follow it with slow cooling, this unstable lamellar cementites shape or any carbides shape all change to globular type of a cementite or any other carbides. So the objective is achieved. You had started with a steel which would have had very high hardness. But just because by changing the morphology of the secondary phase, which was cementite or any other carbides present in it, you have reduced the value of hardness and brought the hardness to a range where softness, ductility, hardness are very good to give you good machinability. This is the first method, but industry does not like this method because of this prolonged, very long holding, which makes it a costly process, which makes it a time-consuming process. Industry doesn't have that much of a time. Second method, students, is the method. This is the second method, industrially used method. What do we have in it? Please remember, whenever we discuss what are the factors which govern the decomposition of austenite, the first factor is the nature of austenite itself. And there we had said nature of austenite means grain size of austenite and the chemical homogeneity present in austenite. And there we had said that chemical homogeneity of austenite factor is only applicable when austenite is to be transformed to pearlite. What's the difference? If the austenite that you are trying to decompose through cooling is completely chemically homogeneous and it is transforming into pearlite, it will always transform into lamellar pearlite. But then if the austenite that you are trying to transform is chemically inhomogeneous, you have deliberately made it inhomogeneous, or by mistake you have kept it chemically inhomogeneous, and if it is transforming into pearlite, it will always transform into non-lamellar globular type of a pearlite. That is exactly the same what we'll deliberately do over here. So now this case was subcritical annealing because annealing temperature was lesser than the lower critical temperature. Students, this is a intercritical annealing because the annealing temperature is in between the lower critical temperature and the upper critical temperature of the steel. We take the steel at the room temperature, which has to be given spheroidization annealing. We take it to a temperature which is more than the lower critical temperature. But please mind, never go beyond 50 degrees in excess of the lower critical temperature. Why? Why this restriction? So that austenite does not become chemically homogeneous. Then you do very slow cooling. From this temperature, you reach another furnace which has been maintained at a low temperature. I should have shown this cooling rate like this because the cooling rate has to be very slow. So when you reach this second furnace, right, again mind it, you have to go below the lower critical temperature, but do not go more than 50 degrees centigrade lower than this, because then the time taken for transformation would become very large. So you heat the steel, take it to a temperature higher than the upper critical temperature, lower than the upper critical temperature, higher than the lower critical temperature, lower than the upper critical temperature, but mind it, never go beyond 50 degrees in excess of the lower critical temperature. Right from when you reach the temperature, start slow cooling and take the steel during that slow cooling to a temperature which is lower than the lower critical temperature, but please don't maintain the furnace's temperature to lesser than to deficient than 50 degrees, more than 50 degrees from the lower critical temperature. Then when you have reached this stipulated temperature below the lower critical temperature, hold the steel for some practical small period of time over here, which experience would show you for a given composition. Finally, slow cool the steel for some period of time, and finally fast cool it, air cool it. No, because if you realize that at this temperature the entire lamellar structure has broken and has become spheroidal or globular, no need of doing slow cooling. You can do slightly faster, that is air cooling from there on. This only experience would tell you, students, that at which temperature the transformation is complete, right? And we come to the third method then. That third method is also not followed in the industry generally. I'll tell you the reason why, because of some material handling issues. In the third method. This third method, students, is called pendulum heating. This third method is called pendulum. I would have mentioned it in the caption of the figure. Yes, pendulum heating. Because you will understand why. So you take, in this third method, final method for spheroidization annealing, you take the high carbon steel or the alloy tool steel at the room temperature, you take it to a temperature higher than the lower critical temperature of the steel. Temperature is generally kept around 750 degrees centigrade. You hold the steel at this heat treatment temperature for some period of time, and when that stipulated holding is complete, so this was achieved in this furnace 1. You were in furnace 1, but now the steel needs to be immediately taken to a temperature lower than the lower critical temperature of the steel, somewhere in between 680 to 700. So the only way how you can very quickly do that is take out the samples from the first furnace, which were at about 750, plunge them into a second furnace which is maintained at 680 to 700, lower than the lower critical temperature of the steel. Now hold the steel samples in this furnace at this temperature for some period of time. The first cycle is complete. Again, from here, take the samples to the first furnace again, to furnace 1. Again, do the same amount of holding. No sooner that holding is complete, again take out the samples from the first furnace, plunge them into the second furnace and do some holding. The second cycle is complete. Keep on repeating this cycle to cycle. Generally, it is said that after about 3 such cycles, all lamellar or non-globular cementite and carbides transform themselves into globular and spheroidal cementite, thereby bringing the hardness of high carbon steels, high alloy tool steels, and making their machinability excellent. So this is all about the methods that are available, students, for doing spheroidization annealing. Then somebody can ask you that why low carbon steels cannot be given full annealing. See, spheroidization annealing brings about a change in the microstructure, and that microstructure now we know, but that microstructure essentially brings down the hardness of the steel. So low carbon steel, students, are already very, very soft because of the low carbon amount in them. And now if you give them spheroidization annealing treatment, this globular type of a microstructure that would come in these steels would make them still softer. So they'll hardly have any hardness in them when you bring them on the machining table. So when you try to machine low carbon steels which were subjected to spheroidization annealing, because these steels have become excessively soft, the cutting tool will, when the cutting tool tries to machine or cut them, it will rather keep on pushing them and not be able to cut them because any reaction is not coming. So these steels become very soft, they become very gummy, and the cutting tool is not able to cut through them. Rather, it keeps on pushing them, providing a lot of heat, which blunts your cutting tool, which damages the surface. So low carbon steels should not be given spheroidization annealing. It is only meant for high carbon steels, steels which have in excess of 0.6 weight percentage carbon, plus any alloy tool steel can also be given this treatment. And fine. So conclusion is that machinability, if for these steels has to be improved, the choice should be spheroidization annealing. For other type of steel compositions, we have already discussed in that table on the second slide that which microstructure will give the best machinability for each of those steel compositions. Right, students. Then next, we come to the next heat treatment process, and students, this is called isothermal annealing, or also sometimes called cycle annealing. and this treatment is just a modification of the full annealing treatment. We had discussed, students, full annealing treatment, very good process, but this annealing treatment has got one major limitation. What is that? It takes a lot of time to get completed, so which makes it very, very costly, and which makes it a process with very, very low productivity. So full annealing generally is not used in the industry until and otherwise there is no other alternative is available. Alternative generally would be normalizing or isothermal annealing. So what is isothermal annealing? Isothermal annealing is nothing but a process to improve upon the limitations of full annealing process. It's a modification over the full annealing process. So what type of microstructure? What are the objectives of giving full annealing? The same. What were the objectives of the full annealing treatment? Full annealing treatment, बच्चों आपको याद होगा, किसी भी कारण से if your steel's microstructure has become very coarse grained or it has been damaged to an extent that microstructure contains Widman statin type of a microstructure in it, तो कभी भी अच्छी मैकेनिकल प्रॉपर्टीज नहीं मिलेंगी. यू विल हैव टू रिफाइन द माइक्रोस्ट्रक्चर. तो रिफाइनिंग द माइक्रोस्ट्रक्चर, इफ कोर्स ग्रेन्स आर प्रेजेंट और द एक्सट्रीम केस विडमैन स्टेटन टाइप ऑफ grains and microstructure is present, you give full annealing. Same, you also can give isothermal annealing. If you wish to induce softness and ductility in the steel, you can give full annealing. Was the case, same is the case with isothermal annealing. The third objective of isothermal annealing would be that for this composition of the steels, their softness, ductility, hardness would give you best machinability if you give them full annealing or isothermal annealing. Why? Because these steels ask for fine grained structure with coarse lamellar perlite. Who gives it? Full annealing or isothermal annealing. And finally, if some internal stresses are present in the steel and they have to be removed, full annealing removes them, so will isothermal annealing. So let's see the procedure now, that how a steel component can be given isothermal annealing process. See students, this is the time temperature diagram. Through you can also see this is one of those processes whose processing can be shown on the triple T diagram. On the triple T diagram. Otherwise, for most of the heat treatment processes, representation of heating, holding, cooling is done on the CCT diagram. But if austenite transformation is happening isothermally, as is the case with isothermal annealing, who would give you a better representation of what is happening during cooling? The triple T diagram. But here now first I am showing you on a simple time temperature diagram that if any steel has to be given isothermal annealing, what would be the processing route? You take the steel at the room temperature at any given heating rate, you heat the steel to the same temperature which you had followed during full annealing. What was that? Upper critical temperature से 20 से 40 डिग्री ऊपर आपको जाना है. This would be done in furnace 1. Why? Because the requirement is कि आप ट्रिपल टी डायग्राम पे जाओ और आप देखो कि आप फुल अनीलिंग से क्या बनाना चाहते हो माइक्रोस्ट्रक्चर में. सपोज द आंसर कम्स, सर वी वांट टू मेक कोर्स लैमेलर परलाइट, और सर वी वांट टू मेक मीडियम पर टेम्परेचर परलाइट, और सर लैमेलर परलाइट, और वी वांट टू मेक सर एक्सट्रीमली फाइन लैमेलर परलाइट. जो भी आपको जैसा लैमेलर परलाइट आपको बनाना है, ट्रिपल टी डायग्राम में जाकर देखिए कि किस टेम्परेचर पर वो वाला परलाइट बनेगा, and choose this temperature. So we have chosen this as the temperature where austenite should transform. But because this is isothermal annealing, austenite will not be made to decompose or transform over a range of temperature during cooling. Rather, it would be transformed isothermally at any temperature below the lower critical temperature of the steel. So I have formed, what is the purpose of heating and bringing it to the heat treatment temperature? Sir, austenite बना लो. What is the purpose of this holding? Sir, सारी जगह temperature uniform कर लो throughout the cross section of the material. Plus ये जो austenite initially बना है heat treatment temperature पर, this is chemically not homogeneous. So through this holding, diffusion would occur and austenite would become chemically homogeneous. Now this chemically homogeneous austenite has to be brought to conditions where it can decompose or transform, and those conditions are bring it टू अ टेम्परेचर लोअर देन द लोअर क्रिटिकल टेम्परेचर ऑफ द स्टील। तो आपने क्या किया, क्विकली इसको ट्रांसफर किया एक दूसरी फर्नेस में, इन फर्नेस 2। हियर दिस इज furnace 2, maintained anything anywhere between 600 to 700 degrees centigrade. See, this is the point, sorry. So I have, this is the point representing this temperature. 600 और 700 के बीच में कुछ भी रखो। 700 पे रखते हो कोर्स लैमिलर परलाइट बनेगा, 650 पे रखते हो मीडियम लैमिलर परलाइट बनेगा, 600 पे रख दोगे फाइन या एक्सट्रीमली फाइन लैमिलर परलाइट बनेगा। जहां जो वाला परलाइट बनाना है डिपेंडिंग अपॉन द रिक्वायरमेंट्स, वहां स्टील को ले आओ। सपोज करिए बच्चों 2 मिनट के लिए कि हम इसको ले आए 610 डिग्री सेंटीग्रेड पर, वहां फर्नेस मेंटेन थी 610 पर, क्विकली सारे सैंपल्स जिनमें 100% ऑस्नाइट है उनको ले आए, क्विकली ट्रांसफर किया फर्नेस 2 में, 610 पे मेंटेन्ड है, यहां होल्डिंग कर दी। होल्डिंग करोगे तो यहां ऑस्नाइट की ट्रांसफॉर्मेशन होगी। ट्रिपल टी डायग्राम बता देगा कितने समय के बाद ऑस्नाइट टूट जाएगा, उसके बाद आप एयर कूलिंग कर दो। ट्राई टू रियलाइज कि कहां तो आप फुल अनीलिंग में यहीं से स्लो कूलिंग करना शुरू कर देते थे और ये आप सारा टाइम वेस्ट करते थे। लुक एट द अमाउंट ऑफ टाइम दैट यूज्ड टू टेक टू कंप्लीट द फुल अनीलिंग प्रोसेस। और जब ऑस्नाइट को ही ट्रांसफॉर्म करवाना है और परलाइट में ट्रांसफॉर्म करवाना है, जिस टेम्परेचर पे ट्रांसफॉर्मेशन कराना चाहते हो, फटाफट सैंपल्स को यहां से उठाकर वहां ले आओ, होल्डिंग करो, चाहे स्लो कूलिंग करो। स्लो कूलिंग तो नहीं कर सकते बिकॉज दिस इज आइसोथर्मल एनीलिंग, मींस ऑस्नाइट विल ट्रांसफॉर्म एट वन सिंगल टेम्परेचर आइसोथर्मली। तो वहां जब ट्रांसफॉर्मेशन कंप्लीट हुई कितने समय के बाद होगी, द ट्रिपल टी डायग्राम वुड गिव यू द एग्जैक्ट न्यूमेरिकल इंफॉर्मेशन ऑफ द टाइम कि सर इतने टाइम के बाद आप स्लो कूलिंग आइसोथर्मल होल्डिंग छोड़ दीजिएगा, एयर कूलिंग करिएगा, पहुंच गए रूम टेम्परेचर पे। दिस इज हाउ इट इज कंप्लीटेड। सो बहुत ही कम समय में कंप्लीट हो जाएगा। दूसरी चीज बच्चों, जहां फुल अनीलिंग करते हुए जब यहां ट्रांसफॉर्मेशन होनी थी बिटवीन द अपर क्रिटिकल टेम्परेचर एंड द लोअर क्रिटिकल टेम्परेचर, ट्रांसफॉर्मेशन होनी थी ओवर ए रेंज ऑफ टेम्परेचर, तो लेमुलर स्पेसिंग में फर्क आना था। शुरू में बड़ा कोर्स लेमुलर स्पेसिंग आना था, एंड में बिल्कुल फाइन लेमुलर स्पेसिंग आना था। लेकिन यहां क्योंकि सिंगल टेम्परेचर पे ट्रांसफॉर्मेशन हो रही है, द रिजल्टिंग लेमुलर स्पेसिंग इन द माइक्रोस्ट्रक्चर वुड बी वेरी यूनिफॉर्म, राइट। और यह भी कहा जाता है कि जब आप आइसोथर्मल अनीलिंग देते हो फुल अनीलिंग की जगह, मशीनेबिलिटी और सरफेस फिनिश भी और अच्छे मिलते हैं रिजल्टिंग स्टील में। तो अगर यही बिल्कुल चीज़ अब मैं आपको ट्रिपल टी डायग्राम की सहायता से दिखाना चाहूँ, सो आई हैव ब्रॉट दैट डायग्राम ऑल्सो फॉर यू, सो यू कैन सी यू टुक द स्टील टू दिस टेम्परेचर, दिस इज द हीट ट्रीटमेंट टेम्परेचर और द आइसोथर्मल अनीलिंग टेम्परेचर। और ये टेम्परेचर क्या है, इट हैज़ टू बी ओके इफ इट इज़ फॉर ए यूटेक्टॉइड स्टील और ए hypoeutectoid steel or eutectoid steel, this is upper critical temperature, sorry, AC3 plus 20 to 40 degrees in excess of it। पहुंच गए आप यहाँ, यहीं आपने कुछ होल्डिंग भी कर ली होगी जो मैं यहाँ नहीं दिखा रहा। यहाँ पहुंचकर ऑस्नाइट बन गया, थोड़ी होल्डिंग की होगी, ऑस्नाइट केमिकली होमोजेनस हो गया। अब आप कह रहे हो कि सर ऐसे टेम्परेचर पर ऑस्नाइट को ले जाओ जिसमें आप उसको तोड़ना चाहते हो। तो यू नो फ्रॉम द ट्रिपल टी डायग्राम, यहां तोड़ेंगे तो कोर्स परलाइट बनेगा, ये रहा बच्चों कोर्स परलाइट। यहां तोड़ेंगे तो बिल्कुल फाइन परलाइट बनेगा, ये देखिए लेमुलर स्पेसिंग कितनी फाइन आ गई। कोर्स लेमुलर स्ट्रक्चर मींस बहुत दूर दूर हैं लेमुलाज और मोटे हैं, लेकिन उन्हीं मोटों को तोड़कर अगर आप ज्यादा जगह में बिखेर दो, दे बिकम फाइन। सो दिस इज फाइन ग्रेन्ड, I have not shown the grains over here. This is fine grained structure with coarse lamellar perlitic spacing, and this is again fine grained structure। अगर मैं grains दिखाता but साथ में फाइन लेमुलर परलिटिक स्पेसिंग। और जैसे जैसे आप बच्चों ट्रिपल टी डायग्राम में नीचे जाते हो हार्डनेस बढ़ती है। यहाँ बहुत दूर हैं लेमुलास तो हार्डनेस कम मिलेगी, यहाँ आपको तकरीबन मिलती है 10 HRC के करीब, जबकि यहाँ पहुँचते पहुँचते हो जाती है 40 HRC की। तो आपको किस तरह की हार्डनेस चाहिए, किस तरह की स्ट्रेंथ चाहिए, आप टेम्परेचर डिसाइड कर लो। इससे नीचे लोअर क्रिटिकल टेम्परेचर से नीचे, ये तो मैंने क्यों लिखा था, वन गलती नहीं की थी। आई एम ड्रॉइंग इट फॉर ए यूटेक्टॉइड स्टील, I am drawing this diagram for a eutectoid steel. For eutectoid steel, upper and lower critical temperature are the same and are designated as AC1. तो इसको मैं AC1 ही रहने दूंगा। So I take the steel to a temperature higher than the upper critical temperature, 20 to 40 degrees, hold it for some period of time, 100% chemically homogeneous austenite is present in the steel. Decide from the triple T diagram where austenitic transformation has to be done. हु वुड डिसाइड दैट आपको कैसी प्रॉपर्टीज चाहिए? जैसी प्रॉपर्टीज चाहिए वैसी लेमुलर स्पेसिंग आपको चूज करनी पड़ेगी। कम हार्डनेस चाहिए, आप अपनी ट्रांसफॉर्मेशन यहां करवा लो। मीडियम परलाइटिक स्पेसिंग चाहिए, यहां करवा लो। मैंने इस एग्जांपल में डिसाइड किया कि नो, आई हैव टू हैव फाइन लेमुलर परलाइटिक spacing, so I took my steel from this first furnace, immediately transferred it to the second furnace. This is furnace 2, this was furnace 1. Here I have held the steel for isothermal transformation of austenite. It takes this much of a time. After this period of time elapsing, austenite transformation would have been complete. No need to do further holding now. Immediately start doing air cooling. आपका ऑस्टेनाइट फाइन ग्रेन्ड फाइन लेमुलर परलाइट में बदल चुका है। आइसोथर्मल अनीलिंग कंप्लीट हो गई है एयर कूलिंग के बाद। हाँ, जितनी फास्ट कूलिंग करते हो इंटरनल स्ट्रेसेस स्टील में डेवलप होती हैं, तो आपको देखना है कि उतनी की ही तेज स्पीड पर कूलिंग करनी है जितना आपकी स्टील बिना सिग्निफिकेंट अमाउंट ऑफ इंटरनल स्ट्रेसेस डेवलप करके निकल जाए, राइट? सो जनरली स्टिल एयर कूलिंग इज प्रेफर्ड. Let's then see what are the advantages and limitations of this annealing, and this is vis-a-vis the full annealing treatment. ये कंपैरिजन हम कब किसके साथ कर रहे हैं? ये कर रहे हैं कि अगर फुल अनीलिंग दे या फुल अनीलिंग की जगह अगर हम आइसोथर्मल अनीलिंग दे दें तो क्या एडवांटेजेस मिलेंगे, क्या डिसएडवांटेजेस होंगे? सो आइसोथर्मल अनीलिंग, क्योंकि आप हीट ट्रीटमेंट टेम्परेचर से स्लो कूलिंग शुरू नहीं करते जैसे फुल अनीलिंग में करते थे, आप तो एकदम उस टेम्परेचर पर आ जाते हो जहां ऑस्टेनाइट टूटना शुरू हो जाएगा. इट सेव्स अ लॉट ऑफ टाइम. It saves a lot of time. So this process is less costly and is more productive as compared to full annealing treatment. Then फुल अनीलिंग में ऑस्टेनाइट टूटता है ड्यूरिंग कूलिंग, तो माइक्रोस्ट्रक्चर यूनिफॉर्म नहीं बनता. लेमुलर स्पेसिंग परलाइट की जो है शुरू में चौड़ी होगी, बाद में कम होती जाएगी, एंड में बिल्कुल ही कम. फुल अनीलिंग में तो बच्चों आप सिंगल टेम्परेचर पर ऑस्टेनाइट की ट्रांसफॉर्मेशन करवा रहे हो, इसलिए बिल्कुल यूनिफॉर्म लेमुलर स्पेसिंग, यूनिफॉर्म माइक्रोस्ट्रक्चर मिलेगा. और तीसरा, मैंने जैसे कहा था कि ये भी देखा गया है, एंड वी डू नॉट नो द रीजंस बिहाइंड इट, कि अगर किसी स्टील की आपने आइसोथर्मल अनीलिंग की है उसमें सरफेस फिनिश एंड मशीनेबिलिटी आपको ज़्यादा अच्छे मिलते हैं एज कंपेयर टू जो आपको फुल अनीलिंग दे रही थी. बट देयर इज वन मेजर डिसएडवांटेज ऑफ आइसोथर्मल अनीलिंग, क्योंकि आपको एक फर्नेस से एकदम सैंपल्स को दूसरे फर्नेस में ट्रांसफर करना है. लार्ज साइज सैंपल्स की आप आइसोथर्मल अनीलिंग नहीं कर सकते. सो दिस प्रोसेस इज रिस्ट्रिक्टेड फॉर यूज ओनली फॉर स्मॉल साइज्ड सैंपल्स. There was no such limitation in full annealing, क्योंकि वहाँ कोई हमने तो एक फर्नेस में आराम से रख दिया, उसी फर्नेस में सब कुछ हो जाएगा. यहाँ आपको ट्रांसफरिंग करनी पड़ती है, मटेरियल ट्रांसफरिंग, which is not easy when the sample size is very large. So this process is only limited for small sized samples. That's the only, but it's a big disadvantage. So this is all about these two more annealing processes we have discussed. One was spheroidization annealing, and the other was, students, isothermal annealing or cycle annealing. So thanks for viewing, thanks for being with me, and probably in the next class we'll take up some more annealing heat treatment processes. Then we'll come up with a lecture on normalizing, followed by hardening, and finally tempering. Thank you so much.